It's 4 a.m. for me, so I'm going to talk very fast to try to stay awake. First of all, I want to thank Steve and everyone else from Foot Squeak for putting on a great conference. So power is something that most developers don't think about, mainly because it's not always clear to know how much power your app uses. So we're going to talk about today how important it is, how you can determine whether your app uses too much power, both on iOS or Android. We're going to talk about the top 5 most common power problems. We're going to talk about how you can test the performance of your app in 25 key areas in only 60 seconds. We're going to show you how you can determine how your app compares to others in Google Play. Going to talk about whether your app is throttling the processor or not. Does it have any graphic performance bottlenecks? Yes. Yes. Oh. Yes, appreciate that. We're also going to talk about whether your app uses the cellular radio in an efficient manner. In fact, most apps do not. We're going to show you how to instrument your code to pinpoint causes of power spikes, automate your power testing, and much more. All this is important because as mobile apps move into new areas like VR and 360 video, performance, system latency, and thermal behavior becomes much more important. I've got a lot of slides, so I'm going to go very fast, but the slides will be available afterwards. So as I talked about earlier, it shouldn't come as a big surprise that battery life is the most important thing to consumers. In fact, it's even more important than the OS, the screen size, and ease of use. These studies were done in 2014, but I have data from 2017 that basically says the same thing. The only real change here is we've seen the number 2 is now camera quality, but number 1 is still power. The last 3 Android releases, the number 1 thing they've talked about is better battery life. So it's something that's very common. One of the reasons long battery life is such a challenge is we've seen a dramatic change in the hardware specs over the last 5 years. We've seen the cores increase 300%. We've seen the screen resolution go up almost 400%. Cellular speeds have gone up almost 600%. RAM has gone from 16 gigabyte standard. The new GS8 has 64 standard. And the big problem here is the battery has only increased its capacity 34%. So it's no surprise that there's some challenges now. The newest devices like the GS8 have a 3K display. In fact, there's so many pixels, it can show 4 simultaneous 1280 by 720 images at once. 540 pixels per inch. There's a new 4K Sony mobile phone that has over 800 pixels per inch. And while that might sound ridiculous, if you've ever worn a VR headset, you will realize that you need a lot of pixels for a seamless experience. But this does have a cost in terms of power consumption. Another reason long battery life is a challenge is on the newer devices, we're seeing incredible mobile data speeds. This is a real network, a real test. And it's a peak speed, real-world peak of almost 1 gigabyte a second, which is amazing over a cellular network. The newer processors have smaller dies. They're now 10 nanometer, which helps. That's about a 25% reduction in power consumption. But the challenge is we're doing a lot more. Most people don't realize that that new GS8 has a 10-bit end-to-end video path, capable of billions of colors, 192K audio playback, gigabit LTE, multi-gigabit 802.11ad Wi-Fi, and multi-user MIMO. So there's a lot of things going on in these system on chips. You might be curious to know where the power goes. The screen is the biggest consumer of power. As a developer, there's not much you can do about that, but you want to be aware of it. These numbers came from Android has an XML file, and there's even an app where you can see these numbers from your device. The data comes from the manufacturer, so it's only good as their data, but it's useful as a guide. These numbers are a little bit inflated, but again, the useful thing is to see kind of where the power is going and which different areas you can affect. Processor at Fmax consumes a lot of power, but as you're going to see most of the time, it's not using much power. Cellular radio, again, when it's active, it can consume some power, so you want to manage it well. This shows you the CPU power at different frequencies. So most of the time, it's not using 1.5 watts. It's actually using about 270 milliwatts, which is very low. So how much power does your app consume? There's a couple different ways you can determine that. You could measure via hardware or software. There's some challenges with hardware, however. First of all, you have to have the expensive piece of gear to do that. Typically, they start at about $800. But the bigger problem is you need to actually break the connection to your battery in your device. And with today's phones, without removable batteries, that's become a lot more difficult. You need to crack the device open, break the connection. It can be done a couple different ways, but it's not easy. Here's an example. If you have an old device like a Note 4, you can just attach little clips onto the battery terminals, so that's pretty easy. But I have a Nexus 6, so I had to break it apart, break the battery connection, and solder in some test leads. You can see them on the right. Something you probably don't want to do on a brand new, very expensive phone, and the chances of you destroying the phone are fairly high, to be honest. Another way is using flat insulated copper tape, but again, you're going to have to break the phone open. So hardware measurement is tricky. Another challenge with hardware measurement is you cannot use the device with the cellular radio in a non-tethered mode, which is something as a developer you want to know. You want to see what's happening with the radio, and you want to use it like a real user. So software measurement's a lot easier. It's free. You can run an app. And as you'll see in a minute, it's actually pretty accurate. So there's a number of different pieces of software that do this. I've listed 4 different ones here. The Android battery app is good for some things. It's good for showing whether you're keeping the processor awake, what the cellular radio is doing, whether the screen's on. But it doesn't show you the actual power use. It only shows you the battery level. So it shows you at the beginning of your game, you were at 85% and now you're at 78. Well, that doesn't really tell you how much power your app's using. So I'm going to talk about a piece of software that Qualcomm makes called Trepn-Profiler. And the reason this is a little more accurate, it actually connects to the power management IC directly, and it reads the current and the voltage and uses that to calculate the power. So the app is in Google Play. It's free. You enable battery power. It's important that you acquire a wake lock. Normally, this is something you don't want to do because it's going to use extra power. But this collects a lot of data every 100 milliseconds. So 100 times a second, it's recording to a database. If you don't keep the processor awake, it's going to lose data and your accuracy will drop. And then you're going to click on Profile App. You can view the data as a graph. You can see in the middle, or you can view the instantaneous and averages. If you're an iOS user, there's some good software called GameBench. It's available free for, I believe, I think you can use it for, I forget what the limit is, a week. My friends from GameBench made me some slides that show you basically how you install it. So first of all, you install it on Windows, Mac, or Linux. You hook up your device, initialize the wireless profiling, and then you're ready to actually use your game or whatever your app is. They mentioned you want to establish some methodology for reasonable numbers. There's some things you can't control, like the battery size and other attributes, but there's a lot of things you do have control about. You want to be aware of the display brightness. They recommend that you match the brightness with 2 devices kind of visually, because the numbers aren't always equal. What's 50% on one device won't necessarily be the same brightness level on another. They also recommend you disable things like cellular, Bluetooth, NFC, location. They also said to be aware of what's running in the background. You want to minimize that. They found in their tests that having Skype logged in, just logged in, has a significant impact on power consumption, even when it's not in use. So I found that to be interesting. Once you've defined your methodology, you're ready to actually do the power consumption. They did some tests here with Super Mario, and they found some of the devices were really efficient. They saw current draws of less than 700 milliamps and an expected gameplay of 4 hours. On some of the older devices with smaller batteries, they've got some older iPhones listed there, and there the gameplay dropped to 2 hours, so a significant increase in power consumption. There's a link here where to get the software if you're interested, and if you have any questions, there's an email address. The bottom line is if you can measure it, you can act on it. I find it's helpful if you first measure your device idle without the app running. That establishes a baseline. Then you want to measure the average power consumed by your app. And then basically now the delta between those is the actual power that your app is using. Next, I find it helpful to compare the power consumption of your app to similar apps. Obviously, if you're in an extreme game, you're going to use much more power than a social media app. So compare like apps. Also, it's very helpful if you try different code approaches. So here's an example how that can be done. Well, first of all, I want to talk about different approaches. So here, I've got a video player app decoding a 4K video. And in the first plot, this is an old version of Trepn. I'm using software decoding. And on the right side, I'm using a hardware decoder. And it's very obvious here which approach is going to be better for the battery life. The software decoder uses 3 times more CPU and 43% more power. So a very clear path in terms of which to go. In terms of the accuracy, because we're reading direct power, the purple trace is the GPU load, and the blue trace is the actual battery power being read. And you can see on the transitions there's a very high correlation there. I talked earlier about markers. You can put intents in your code and numeric markers or labels, and you'll see those on the graph and also in the static view. So here I have a web browser, and if you look at marker number 1, there's a web page that's being loaded, consumed, looks like about 1.1 watts of power. After that, the page is scrolled. That was about 900 milliwatts. Scrolling paused, the power dropped to 300 milliwatts, significant reduction there. Then a second page was loaded, and that was only 500 milliwatts. So that page was much less intensive in terms of the amount of things on it, much less power consumed. So it's a very easy way that you can put markers at any point in your code, and you can see the average power change. In terms of accuracy, I did some tests. I ran a script to set the screen brightness at different levels. And then I had a Monsoon, which is a hardware power measurement connected to my Nexus 6. And I was also at the same time running Trepn software on the Nexus 6. And you can see the actual power measured at each screen brightness level, and you can also see the error. So in most cases, it's 2-3%, so very accurate. It is on target, right? So you are adding to the load, and that's going to be inflating the power ratings probably about 15%. So you do want to be aware of that. This shows how you can do that type of automated testing. In this particular example, instead of setting screen brightness, I'm forcing the processor at a different frequency. And these are all done using ADB commands. And then on the right, I can see the purple line is the different frequency steps, and I can see the power on screen. You'll notice power is really spiky. It looks almost random. So sometimes it helps if you zoom out, you can get a better idea. But after you work with it more, if you look at the averages, you can get a better idea how to really interpret it. So power measurement best practices, if you're using software like Trepn or some of the other ones I talked about, it's important that you remove your USB cable. Now as a developer, normally you're going to be connected because you're running ADB commands or scripts. But for power, you can't do that because if you're charging a device, you're not going to be able to measure accurate power. So you need to disconnect it. If you need to script or do ADB, you can do ADB over Wi-Fi. That's easy to do. Make sure the CPU is awake at all times. We talked about that earlier. Minimize your background processes. That's really important. You also want to make sure you're using a device that reports accurate power. It used to be that was easy, and pretty much every Nexus device did. Two things have changed. It's made it very difficult. Number one, some of the processors, the newer processors, only report power updates every 30 seconds. It's not accurate enough to do good averages. A device like a Nexus 6 reports it 100 times a second. So using an older device like a Nexus 6 or a Nexus 7 is very useful. Also, it's better to use Android 5 or 6. The newer Android versions are blocking thermals and power, so they made it much harder for people to get that information. I just bought an old Nexus 7 on eBay, and I use that to do my power measurements. The other nice thing is I've uninstalled all the apps on it, so there's not much running in the background. It gives me a much better idea what's really happening. Turn off everything you don't need. That was a recommendation that GameBench mentioned as well. Normally I'll put it in airline mode and then turn on Wi-Fi and turn off everything else I don't need. Minimize the screen if you can. I'll run it at a lowest possible level, and then there's a link to a ton more best practices. So what are the most common problems for power? There's 5 of them. Number one is this inefficient use of cellular radio and Wi-Fi network. We're going to talk about how to fix that in a minute. 2 is preventing the processor from going to sleep. That's not as big of a problem now as it used to be. 3, keeping the display lit too long. That used to be a big problem. You don't see that much anymore. 4, not using all available system resources. That's still a big problem. And 5, you see some apps taking too many GPS fixes. So how do you use a cellular radio efficiently? A lot of apps have problems, especially social media apps. The reason this is such a big deal is when the cellular radio is active, it uses a fair amount of power. In this example, it's about 300 milliamps. And then it goes to a idle state, and it stays in that state for up to 15 seconds. And it's still at a fairly high power level. It's at 150 milliamps. And then finally it goes into a dormant state. So that's kind of referred to as the long tail. You can see it here. This is some software called AT&T makes. It's called Arrow. They may have renamed it to Video Optimizer, but it's free. And you can see the data on the top, the packets uploaded and downloaded. You can see the cellular radio, that red triangle kind of ramp up. It stays on in its high power state for 4 seconds. And then it basically stays in this kind of intermediate state, in this case, for it looks like 14 seconds. So most of that time is actually wasting energy. So you really want to be aware of how you group your data. We're going to talk about some ways to address that in a minute. It also does a whole list of best practices. Here's a well-behaved app. It's Google News. And you can see everything's green checks, no real issues there. I put another news app, I won't mention the name here, and I can see a lot of red X's. This app isn't doing texture compression properly. It's sending duplicate content. It's got a lot of issues. And you can click on each of those and it will give you best practices, how to address those issues. Really helpful app. This is a screen view from Trepn. It also shows you mobile data states. So you can see the top is the power level, and the bottom is the data state. So there's actually 6 different data states: off, connect, dormant, idle, send, and receive, and then a combination of send and receive. So the first 6 markers, the red markers at the top, show when the radio goes from idle to transmitting. In each case, the power increases between 500 milliwatts and 1.2 watts. Significant increase. What I did to force that is I was on Google Drive and I was accessing a file, a couple different files over a period of 90 seconds. Notice the cellular radio only goes from idle to dormant twice in 90 seconds. So we're kind of illustrating what we talked about before. You can see that long tail with the horizontal red markers. When it does actually go into a dormant state, you can see that with marker number 7, the power decreases 600 milliwatts. So you can see exactly what's happening on the radio when you run your application. So this can be really helpful to see if you have a problem here. It's fairly easy to address this problem just by bundling your packets. So if you send 3 different groups of packets, you can see the transmission time for the radio on the left. By bundling the packets, the transmission time is significantly reduced, and that's going to allow it to go into dormant more often and faster. You can also use Android Job Scheduler APIs. You can see on the top, mobile radio, it's before the Android Scheduler was used. And there's a lot of little blips up there. And with Android Scheduler, you can see there's more contiguous data. That will have a big impact on reducing power for the radio. Another thing you can do is wait for the right connection. Don't send large amounts of data if you're on a slow connection. I like it when apps actually give you a choice. Either wait for Wi-Fi or only do high data when it's charging. Something much appreciated. That's important because I have a bad cellular connection here, and I can show kind of this extreme case where downloading large files over Wi-Fi consumes much less power. So the power before the download was about 700 milliwatts. The power during the download was 3.2 watts. That's a 2.5 watt increase. By going to Wi-Fi, I saved 11 minutes in time. It's faster. I also saved 68 megabytes of data, and of course I saved a lot of battery life. So it's something you want to be aware of, something that's fairly easy to control. Does your app have problems consuming too much data? Your app itself is probably not the problem, but if you have analytics or ads, you might be surprised how much data is consumed. There's an app I'm going to talk about in a minute called App Tune-Up Kit, but basically I ran 3 different apps for 1 minute. The first is Google Photos, and it consumes 7.2 megabytes, but that's expected because it's got thumbnails, it's loading a bunch of photos. The second 2 were games. The first game in 1 minute, I made sure that the game was fully loaded before I did my test. So basically, everything was loaded, it was ready to run. I played the game for 1 minute, it used 161 megabyte in a minute. Significant amount of cellular data. The other game used about 26 megabytes in 1 minute. That's a lot of data, considering the game was not loading at this time. So it's hard to say what they're doing. Are they loading ads? Are they, who knows? But they're using a ton of data. Analytics and ad services vary greatly. There's sites like Criticism that show you the response times and error rates, something to be aware of. There's also other sites that will show you what other apps and other SDKs, other websites use in terms of SDKs. So for example, the BBC News app has 23 different SDKs. It's interesting to see if you can find an app that is a category leader, something that you think is a well-run app. Look at what they're using for analytics, what they're using, and that can be pretty helpful because they've spent a lot of time sometimes determining what are the best. Does your app keep the processor awake? There's a couple ways to look at this. Battery Historian's something that Google makes. It's available free. You can see the wake locks on the top. You can see the kind of battery level, black line. There's a bunch of other things that are shown as well. It's interesting to see things like Wi-Fi scanning. Even though you're not using your device, you'll find a lot's going on in the background. You can also see this is just part of the Android OS. I like this screen because it shows you on a per app basis how much mobile data is received and sent and how long the CPU is awake. So if we look at some of these keep the processor awake, if you look at Foursquare, the processor's awake for 8 minutes, even though the app was never launched. It was never really being used. it's still keeping the processor awake, which is going to consume a lot more power. Don't acquire Power Manager wake locks unless you really need them. Use minimum levels, release them as soon as possible. Consider using Alarm Manager in situations where you want to have your app run code at a specific time. Android's made this a lot easier than it used to be. In terms of using the display in an efficient manager, full wake locks, obviously you don't want to use those. If you use flag, keep screen on, that's better. I found that dark themes consume half the power of light themes. So something to be aware of. It's nice to give users a choice, especially if they want to maximize their power. Does your app use all the system resources? There's a lot of different ways to determine this. Pretty much any profiling software will show you. In this particular case, I'm showing Trepn. This app is actually maxing out all 4 cores, but almost ignoring the GPU entirely, so that's something that's not good. You want to be aware if your app's GPU or CPU bound. Again, there's a lot of different ways to determine this. This app is obviously GPU bound. You want to know whether you're using all the cores or not. I'm surprised how many apps don't use all the cores. It's very easy to see. There's a way to ensure that you are using the cores, and there's also a way to ensure you're using the different hardware resources available. You want to run the right task on the right processing engine. So certain things are best on the CPU, like game AI. Other things obviously are better on DSP, object detection, audio. Things run very well on DSP. And other things run better on the GPU. Ideally, you're going to be using everything that's available to you. That will increase the processing power, and also in many cases it will lower your power. Qualcomm makes something called Symphony SDK that can be helpful for people who are doing native code. It allows you to use parallel processing to make sure that you're spreading the load across the different cores. With Core Affinity, you can specify whether big or little cores are used for things. There's Power APIs where you have control over, do you want kind of a maximum performance or do you want a maximum power mode? To give you an example of this in action, this was a security camera that did software video encoding, and it used a mid-range chipset. And that chipset had 4 big and 4 little cores. They found that when they ran this application, fairly quickly they hit a thermal alarm because they were doing software encoding even though the chip supported hardware encoding. So it's less efficient. They were hitting a thermal, the processor frequency was dropping, and as a result the frame rate dropped. And the process continued until the frame rate was about 18 frames a second, which was unacceptable. Using Symphony, they tried a couple tests. First of all, they tried 4 little cores only. And they found that it solved the thermal problem. There were no more thermal alarms, but the frame rate was only 23 FIPS. So with just a couple lines of change, they set it to use the 4 little cores and the 2 big cores. And they got a thermal rate consistently of 30 frames per second, and they had no thermal limits. So it's a fairly simple fix. You can save a lot of power by offloading to a DSP. This should give you some examples. It extends music playback time 50% to 60 hours. If you do something like sleep tracking, it has a dramatic increase on battery life. Facial image recognition type things, significant increase. I'm doing a lot now with VR headsets, and we're running a lot of things. We have 6-off tracking, and we're doing all that in the DSP, and it really helps to reduce power. You want to be aware of GPS fixes. I use Twitter a lot. It used to be every time I would launch the app, it would do a GPS fix for no reason, even though I wasn't ready to post, even though there was no reason for it to do that. It would do it, and that would consume power. As we saw before, I think it was about 300 milliwatts. So if you do that enough, it does add up. Only take a fix when you need it. Use coarse fixes when possible. They use less power. Let Location Manager find the best provider. If you can't find a satellite, have a timeout period. I've seen apps that will go continually looking for a satellite, just wasting power. And also let users disable location tracking without crippling their device. Android O does help in this area. There's some new background limits that are in Android O. And it limits background in 3 areas: implicit broadcast, background services, and location updates. There's more information here if you want to click on those links. All these slides will be available afterwards. How to make sure your performance remains high at all times. There's a lot of good profiling software. If you're an iOS user, I'm sure you use Xcode Performance Tools. ARM makes something called Streamline that's very good. I mentioned GameBench earlier. Android users are probably using Android Studio. There's built-in performance profiling there. Intel System Studio is very good. Qualcomm has a profiler called Snapdragon Profiler. If you're a Unity user, they have some built-in profiling. The reason you're going to profile is the things I talked about before. You want to know if you're CPU or GPU bound. You want to know if you're throttling the processor. You want to watch for memory leaks, performance bottlenecks. Make sure you're using all the cores. One of the problems with profiling is you get a lot of information, a lot of graphs, and it doesn't always tell you how to act on this data. So we created an app that basically tests 25 different areas in 60 seconds. So the idea is you launch it. It's called App Tune-Up Kit. And you select any app, and you use it like normal for 1 minute. So in this case, I'm playing a game. I play it for 60 seconds. The app will come in the foreground, and it will give me some stats. You can see on the left is the app I was testing. And at a glance, you can tell, you may not know that 3.8 watts is good for a game, but this tells you it is good. It's green. It tells you it's good. And then it shows you other categories like CPU usage, GPU. And again, watch for red, yellow, green. It's like a stoplight. There's an app on the right there that you can tell uses much more power. And in that particular case, it's higher than expected. By default, it compares to the top 20 apps. So it's important once you do a test that you set that category. So this app is a benchmark, and you can see the change. When I set it to top 20 apps, it's yellow, indicating there's a power problem. When I set it to benchmarks, it goes to green, because as far as benchmarks go, those are reasonable numbers. So it can save you a lot of effort. There's a long, long detailed report if you're interested. It will show you if all the cores are being used, how much data, a lot of stuff. For this benchmark, I can see the peak power is 6.2 watts. That's a lot of power. If you have a game and it's going to use 6 watts, your battery life is going to be impacted. We recommend you save the results in the upper right, and then you can view 2 different save sessions, and it will give you a detailed comparison. Here I'm comparing Asphalt 8 and Need for Speed, and I can see how they compare in different areas, and then there's a delta on the right. For fun, I loaded the CodeMobile conference app, and I compared it to Google I/O, their app, and I found it actually stacked up pretty well. In fact, it consumed a little bit less power than Google's Google I/O app. There's some recommendations. This is a part of the app that was never really finished. It's a good starting point, but it's kind of a beta feature right now. I did some tests with popular apps. I found this was kind of interesting. I was surprised to find that a flashlight uses 10 times more CPU than a media player app. So iHeart's a good example of a well-behaved app. The CPU temperature is very low, almost no CPU and GPU. They're offloading everything to the DSP. And as a result, very little power consumed. And that 0.93 watt is not the app power. That's the whole phone with this software capturing. So it's extremely low. Super bright flashlight, 1.5 watts. I don't know what they're doing, but look at the processor temperature. Look at the CPU, GPU. That's a big problem. There's something going on there. Here's 2 different news apps. You can see one is very well behaved, under 1 watt. very minimal CPU, GPU. Processor is almost room temperature. And then there's another app that's using a massive amount of CPU and GPU. And we're not playing video. It's just static news feed. No reason for that, some serious problem. Here's two different games. I've got a casual game and an extreme game. And the casual game is actually using more GPU than the extreme game. Big problem there. They're probably using middleware on the casual game, and the extreme game is probably not using it. There's some best practices here. If you're going to run App Tune-Up Kit, it's very important that you follow all these steps to get the best results. If you do, you'll get you should get reproducible data. All right, throttling is something that you really want to be aware of because it has a big impact on performance. Here's an example. I'm running Snapdragon Profiler, which is free software. You can see this on any of the other ones I recommended as well, like ARM Streamline or Intel's tool. If you look at the top, we see the frequency of all the 4 cores. I'm running a processor-intensive app for a long period. And we can see the die temperature is rising to 65 degrees centigrade. That's fairly hot. As a result, the thermal limits management system is going into place, and it's dropping the CPU frequency in half. So obviously, the performance is going to drop. And I don't show frame rate on here, but frame rate's going to drop probably 50%. After 60 seconds, the temperature goes down, and it recovers. But you never want to reach the state where you're throttling the processor. I find that a lot of apps have problems with graphics, not using graphics in an efficient manner. I'll give you some examples. This is some other tests done with Snapdragon Profiler. There's a trace capture mode where basically you go through, this tells you step by step how you do it. And basically you're just capturing a trace. So just follow these steps. For fun, we captured a trace on an app with 200 million daily users. So this is an extremely popular app. And we tried some different settings. When the effects were enabled, we noticed that 2 threads were used, which is not a problem in itself, but we noticed a lot of GMEM loads. GMEM loads are basically when the GPU is accessing system memory to fill a tile. And this is something you want to avoid. If you look at those red areas, those are all GMM loads. And there's something that you can see easily here. This also shows you things like what's happening with the CPU scheduler, exactly what's running at any given time. So obviously you want to avoid these. Don't use patterns that are going to cause a situation. The easiest way to prevent this is to ensure the frame buffer is cleared immediately after every call to the GL bind frame buffer. Easy to do, very effective. There's more information here on how to resolve that. There's also a snapshot capture. And this is something that all the profilers do. You can basically capture a frame and then analyze it. So I did the same app and found there were a lot of issues here as well. There were heavyweight GPU calls. There were a bunch of queries that they didn't need to happen. And also, I noticed in one frame there were 80 EGL get error calls per frame. So there were some debugging things that were on that shouldn't be on. So you only want to use the GL get error calls when you're in a debugging mode. It's using a lot of graphic API calls unnecessarily. So this is some more suggestions. If you minimize your draw calls, so batching them, that reduces overhead. And again, you can get these slides. John Carmack recently did a really good blog article on graphic optimization. Basically, by following these 2 tips, you can increase your rendering speed by 40%. Register to each frame buffer once if possible. Call GL and validate frame buffer after attaching a frame buffer. This tells the driver you can safely skip the read even if you don't clear. So something that's fairly simple to do and has a huge effect. This shows you if you do graphic optimizations, you'll see a big impact, reduction in processor usage. You'll see temperature drop. And in this case, the frame rate went from 3 to 30 frames per second. So highly effective. So just recap on power saving tips. Use wake locks only when necessary. Close your sockets when done. This can reduce network power up to 20%. Group network activity or use Android's job scheduler APIs. Try to use all available system resources, all your cores, your GPU, DSP, everything available. Avoid processor throttling and GMEM loads. And render to each frame buffer once if possible. So most Apple apps, surprisingly, do not use the processor, cellular radio, or other system resources efficiently. This wastes power, which has a negative impact on battery. That's one of the reasons all of us are always struggling to get through the day on our devices. It's very easy to measure power consumption. If you can measure it, you can act on it. You should know how much power your app uses. You should know how much your competitors use. And you should know how to improve it. Solutions are readily available. They're easy to do. And better battery impact, better battery life is obviously going to make for happier users. I got a bunch of links here that you might want to look at later. Some kind of follow-on materials. Talks about hardware power measurement, software best practices. There's the article I talked about from John Carmack, which is worth reading. And that's really it. I think I have 2 minutes for questions if anyone has anything. All right. Thank you very much. I'll be around if anyone has any more questions later.